Hello, my name is Daan de Geus and I will present our work called Content-Aware Token Sharing for Efficient Semantic Segmentation with Vision Transformers. In this work we present Content-Aware Token Sharing, or CTS, which is a token reduction method for vision transformer-based semantic segmentation networks. We reduce tokens by letting redundant patches share a token, where redundant patches are patches with similar content identified by a lightweight policy network. And because the network makes predictions using a reduced set of tokens, we improve efficiency. And with our method, we are able to achieve token reductions of up to 44% and thereby increase the throughput by up to 110%, all while not impacting the segmentation quality. And finally, our CTS method is generally applicable to VIT-based semantic segmentation networks. So in this work, we consider vision transformer-based semantic segmentation networks, where all patches are processed as unique tokens, as visualized in this image. However, we observe that many patches contain the same semantic class, as visualized here. Therefore, these patches contain redundant information, but they still get a unique token, which is inefficient. Therefore, our hypothesis is that it is possible to reduce the number of redundant tokens to improve efficiency without decreasing the segmentation quality because we only reduce redundant tokens. However, there are also challenges. Specifically, each patch requires a prediction because we do semantic segmentation. And therefore, redundant tokens cannot just be discarded. And secondly, if redundant tokens are merged, it should be easy to unmerge them again because we need to make a prediction for each patch, each original patch. To test our hypothesis and address these challenges, we propose content-aware token sharing, where we first identify 2x2 neighboring patches that contain a single class, and then treat these neighboring patches as redundant patches. Subsequently, we let these redundant patches share a token. And finally, at the output, we unshare these shared tokens because we need to make predictions for semantic segmentation. The first step in this process is to identify which 2x2 neighboring patches all contain the same single class so that we can let them share a token. And we do this with a lightweight policy network. So how do we learn this policy network? How do we generate this ground truth? Well, we take an input image and we take a grid of 2x2 neighboring patches as visualized here, and we take the corresponding semantic segmentation ground truth, and we identify which of these 2x2 neighboring patches contain just a single semantic class. And if they do contain just a single semantic class, the ground truth of the policy network is true, and when they contain multiple classes, it is false, so that when the policy network predicts a positive prediction for a certain 2x2 patch, this means that this patch only contains a single class and that this set of neighboring patches should share a token. And because this is such a simple binary classification task, we can solve this with a lightweight policy network. And this is important because we need to keep the efficiency improvements that we achieve by token reduction. Well, once we have identified which 2x2 neighboring patches contain the same semantic class with our lightweight policy network, we can let them share a token. And we do this by downsampling these 2x2 patches to 1x1 and projecting them into a token as conventional. Then we end up with a reduced set of M tokens. Subsequently, these remaining M tokens are fed through the VIT as usual. So we can use any conventional VIT-based semantic segmentation model. And at the output, we end up with M tokens. Then, because we need to make predictions for semantic segmentation on the set of original patches, we upsample each shared token and divide them back into 4 individual tokens to end up with n tokens corresponding to the n original patches. Then finally, we predict semantic segmentation using these n unshared tokens. We evaluate our content-aware token sharing on multiple data sets and on different models and backbones, all to show that it's generally applicable. In the first experiment, we vary the token reduction setting, which means that we vary the number of tokens that are reduced. And we find that as we increase the token reduction, we also improve the throughput, which is expected because the semantic segmentation network needs to process fewer tokens. We also find that until a 30% token reduction, as highlighted here, the segmentation quality does not drop, and the throughput is significantly improved. Moreover, the mean IOU for our content-aware token sharing is much better than for random token sharing. This shows that it's possible to improve the throughput by reducing the number of tokens while maintaining the segmentation quality, but that it's very important to carefully pick the patches for which we share a token, which we do with our content-aware token sharing. Secondly, we also do experiments on different backbone sizes. For instance, in this case, VIT tiny, small, base, and large. And we find that we get consistent throughput improvements, as shown in this figure. Moreover, these throughput improvements are achieved without impacting the segmentation quality, which was the goal of this work. Additionally, we also do experiments on different data sets, in this case on Pascal context and on cityscapes. And we also again find consistent throughput improvements. We find that the segmentation quality is not impacted. And especially for cityscapes, we find that we can achieve an even higher token reduction setting, simply because cityscapes has a relatively low dataset complexity, meaning that more tokens in a single image can be shared. To conclude, we presented content-aware token sharing, which reduces redundant tokens, thereby improves the throughput, all while maintaining the segmentation quality, as can be seen in these predictions here, which are generated by networks that apply content-aware token sharing. And finally, our CTS is generally applicable. Thank you very much for your attention. Come have a chat during the poster session and have a look at our project page and code.